This video presents our work, Manifold-constrained Hamilton-Jacobi Reachability Learning for Decentralized Multi-Agent Motion Planning, and its demonstrations in simulation and real-world experiments. We begin with a brief overview of our proposed framework. Our goal is to solve safe decentralized multi-agent motion planning under task constraints. For example, service robots must hold cups upright when they move to prevent spillage. We first formulate multi-agent collision avoidance as a Hamilton-Jacobi reachability problem. To account for the influence of the manifold constraints, we derive a manifold-constrained formulation of the original reachability problem. As we show in the paper, without this manifold-constrained formulation, the learned value function can be over-optimistic. Then, to solve the reachability problem for high-dimensional systems, we extend learning-based pipelines to manifold-constrained settings and leverage structures of the problem for efficient training. Finally, we incorporate the solved value function as a safety constraint to formulate a receding horizon trajectory optimization problem that generates decentralized motion plans that are both safety-aware and task-feasible. Now we present demonstrations for our method. We first demonstrate our method solving a multi-agent object-carrying task where subteams of robots collectively transport objects to their respective goal positions while avoiding collision. The manipulators are constrained such that their end effectors' orientations are fixed. We then demonstrate our method solving a cup-holding task with 2 UR5 manipulators, as well as 5 UR5 manipulators. The robots must keep the cups upright while moving from their start to goal configurations without collisions. The goal configurations of the robots are shown in transparent green, and the 5 manipulator video is shown at half speed for clarity. Furthermore, we design a doorway crossing problem for manipulators. It imposes various constraints on their end effector poses and includes a narrow passage, making it particularly challenging. However, our safety constraint prevents the robots from colliding by enforcing one robot to wait until clearance. Finally, we demonstrate our method-solving dual UR5 cup-holding tasks on real robots, where goal configurations are shown as transparent models. In both cases, our method helped the robots reach their goals by avoiding collisions with each other. As we are using velocity control, robot motions can however be jittery when the safety constraint is acting to avoid collisions. We are actively working to address this limitation in future work. Thank you for watching.